Newton's law. There are three laws that Newton came up with. I'm going to go through the second one first, then I'm going to deduce the first one from the second one, and then I'm going to go over the third one. So Newton's second law is defined as follows. This little symbol refers to the Riemann sum, so it means sum, which means we need to add. This refers to a new concept, which is known as a force. And you will notice that I put a little arrow on the force, which means that this can be described mathematically by a vector. This is an equal sign. This little m refers to mass, and this is our favorite acceleration. So on the right hand side we have an acceleration which is a vector. We multiply this vector by a scalar, which is the mass, therefore overall this is a vector. Therefore on the left hand side, since we have an equal sign, this must also be a vector, and therefore the force must also be a vector. Okay, let's check out first the units of this new concept of force. If we have an equal sign, the units on the left hand side must be the same as units on the right hand side. What do we have on the right hand side? We have an acceleration whose units are meters per second squared. Then we have a mass whose units are kilogram. Therefore on the right hand side we have kilogram meters per second squared. Hence the units of the force must have the same units. Therefore force in physics has the units of kilogram meter per second squared, and we usually define this as N, or Newton. So the magnitude of a force is usually expressed as 2 Newton, 3 Newton, 4 Newton. So in problems, if you are given quantities of acceleration and mass in gram or centimeter per hour or centimeter per second squared, and you want to calculate the force, you want to make sure that you convert all your units into kilogram, meters, and seconds if you want to use Newton as units of your force. If you don't want to change units, then you have to express your force specifically in terms of whatever units you kept for mass and acceleration. Okay, so what does that tell us? This pretty much tells us that every time you have a system whose mass is m, if you apply a force into that system, this system will have a particular acceleration, a. So this is a nice linear equation which means that if you plot f versus a, you know you're going to get a straight line whose slope is pretty much the mass. That is, if you apply a small force, you're going to get a small acceleration. If you apply a bigger force, you're going to have a bigger acceleration. So as you keep increasing the force, you're going to linearly increase the acceleration that the system will be subjected to. This little m also is sometimes referred as inertia. That is, if the mass increases, then the slope would increase. So let's say this refers to a small mass. If you're dealing with a bigger mass, then this would look like this, a bigger slope. That is, if you apply, so let's say this is the bigger mass, this was our original mass. If you apply a particular force to both objects, the force of the big mass will have a particular acceleration, a1, while the same force applied on the smaller mass will have an acceleration a2, which obviously is bigger than a1. Therefore, the mass acts like a resistance to acceleration for a given mass, which is how inertia could be defined. So inertia is concept that represents the opposition to acceleration. The bigger the mass, the harder it is to be accelerated. The smaller the mass, the easier it is to accelerate an object. So keep in mind that concept as it will come back in rotation, and we will add another property to it. But whenever you're doing translation, inertia can be associated with the mass directly. So this is the second law. Another nice property of the second law is the following. If you have a particular particle of mass m and you apply a force F to it in this particular direction, let's say of magnitude of 1 Newton, you know that this particle will be accelerated with an acceleration of magnitude 1 Newton divided by, say, if it's 1 kilogram, 1 meters per second squared. So according to this formula, we're able to calculate the magnitude of the acceleration. What about the direction? Since this is also a vector equation, it follows that whatever direction the force you apply, the force that you choose, applied to that system would be exactly the same as the direction of the acceleration. Now if you have two forces, one going like this, F1, and let's say one going like this, F2. Since you want to take the sum of all those forces, first you need to calculate the resultant force. So you're going to add those two vectors. So remember, F1 and F2 can be moved. So if I rewrite F1 from here, and I'm going to move this vector F2 like this, then this would be my vector sum, or my resultant vector, which is nothing else than the sum of F1 plus F2, which is my left hand side. This will give me the direction of the acceleration of that particle. So for this particular case, if I apply two forces, F1 and F2, to this particular system of mass m, I know that the acceleration direction will be in the same direction as my resultant force, and in this case, horizontal. Let's look at the first law. The first law would be the case where, let's say I'm applying a force F1 in this direction. Let's imagine that I pick 1 Newton, and then instead of applying another force F2, say in this direction, I'm going to choose it such that its magnitude is exactly the same as F1, but its direction is opposite. Therefore, F1 is going to be equal to minus F2. Now, those two forces F1 and F2 are being applied on my system. Since I need to add all those forces, I need to add F1 and F2. Let's add those two. I have F1 plus F2 is equal to ma. Since F1 is minus F2, let's plug that here. Then I end up with F1. Oops. F1 is being replaced by minus F2, so minus F2 plus F2 is equal to ma. And this obviously gives me the zero vector is equal to ma. Now since we are only going to be dealing with particle of positive and real mass, then m is always strictly bigger than 0. Therefore I can divide that one equation by m, and I end up with a is equal to 0. Therefore it is possible that the sum of all my forces end up being 0. In that case, my system is not being accelerated. And I know from kinematics that if a is equal to 0, then dv dt is equal to 0. And if dv dt is equal to 0, it means that there is no change of velocity with respect to time, which means that v is a constant. This is the first law. The first law is telling us that if an object is not subjected by any force, or that the sum of all the forces acting on it is equal to 0, this system will not be accelerated. We call this situation, or this particular state, equilibrium. Another way of rephrasing the first law is that if there is an object which is already moving at a particular velocity, which is constant, if there is no force acting on this particle will remain with the same velocity. But as soon as a force is going to be applied to this guy, and this force is non-zero, then the velocity will change, the acceleration will be non-zero, and then we're back to the second law. So that was the first law and the second law. So let's summarize. Second law, sum of the forces is equal to ma. That's the most general case. It could be that either if you're dealing with only one force, this is zero, no force, or you have several forces still acting on it, but the resultant force, that is the sum of all those little forces acting on the object, and them being zero, then it means that the right hand side is equal to zero, and therefore A is equal to zero, which means that V is a constant. This is the second law, and this is the first law, and this is also known as equilibrium. So this is quite important, because if V is a constant, V can take any value. It's just that that value doesn't change. So V can be 0 meters per second, or the speed could be 0, or the speed could be 2 meters per second, or the velocity could be minus 3 meters per second. If the sum of the forces is equal to 0, this velocity magnitude doesn't change. So a system could be moving at constant velocity, it would still be at equilibrium. Or this system could be at rest, and again, this system would be at equilibrium. In other words, there is no way for Newton's second law to differentiate a system from being at rest, zero velocity, or moving at any value. The second law can only tell us whether a system is accelerated or not, but it cannot tell us any information about the velocity itself. In order for us to do this, we need to go back to kinematics equation. So remember that when we say that the system is at equilibrium, which is also known as static, it means two possibilities. Either the system doesn't move, which is the case where V is equal to 0, or the system is moving, but it's moving at constant velocity. So there is no way for the second law to differentiate from this case to this case. All those cases fall under the first law. Okay, third law. Third law is a little bit different from the first two, and it usually applies when we're dealing with composite system. The major difference between the first and second law and the third law is that the first and second law is applied to a particular system. Remember that the first law is this times A, which is 0, and the second law is this, where A is not 0. When we apply this technique, we need to always ask ourselves the question, to which system are we going to apply all those forces? Or if I'm looking at a particular system and trying to figure out all the external forces acting on it, I need to be very clear on what my system is. So the first thing you need to ask yourself is, what is my system? Once you're very clear on what system you're selecting, then you know that this M is the mass of your particular system. And those forces are all the external forces acting on that system. One side note, all those little f, sometime in books you will see this, ext. They refer to what we call external forces. So when you're dealing with a system, you're only concerned about the external forces acting on it, which means that the source of that force must come from entities which are outside your system. Now, if you're dealing with a case where you have two systems connected to each other, let's say an object pulling on another object, and this object, let's say, is pulling with a force T or F. We have three objects in this system. We have object 1, we have object 2, and we have the string in between, and we'll assume that this string doesn't stretch. So technically we have three different systems. If you want to apply Newton's first or second law, then you will apply it to either system 1, system 2, or system 3. If you want to apply the third law, you will always apply the third law at the junction between two systems. So the third law is not being applied to a system. The third law is being applied to the connection between two systems. That is, let's look at the case of object 2. Object 2 is obviously being pulled by the string, which itself is connected to object 1. So if you imagine yourself being object 2, you will feel a force coming from the tension, and that force is obviously in this direction. Now this force is not F, because F is only applied to system 1, not to system 2. So we need to give it another name. Let's call it T. And at this point, we have no idea how T is, or the magnitude of T. So the external force in the x direction for this particular case would be the force due to the string into the object 2. And this force is going towards the right. That would be from an analysis or applying Newton's law to object 2. Now let's do the same thing and apply the second law to object 3, which is the string. So imagine that you're the string. Something is pulling you, so let's say your head is over here and your feet is over there. Imagine that you're the string, you will feel something pulling you in this direction, and in this case it would be object 1. And then if object 2 has some mass, it will try to drag you on the other direction. So as far as 3 is concerned, it will feel two forces, one going towards the right, which is due to object 1, the other one going towards the left, which is due to object 2. Again, we have no idea what those forces are, so let's call it P and R. So P and R are the two forces, external forces, acting on the string, while T is the external force acting on system 2. So we've just applied Newton's second law to system 2 and system 3. The third law comes in if you're interested in the relationship between this force and this force. So in order for us to use this third law, we want to be concerned about the junction between object 2 and object 3. And at this point, Newton's third law tells us that this is an action-reaction pair. In other words, the force P, which is the force due to object 2 on object 3, is exactly the same in magnitude as the force T, which is the force due to 3 into 2. The only difference between those two forces is their direction. So their magnitude is the same, but their direction is opposite. Therefore, mathematically, this is the relationship between the two. In other words, since P was the force of object 2 into object 3, and T was the force due to object 3 into object 2, then the third law is telling us that F2 into 3, or F2 from 3, is equal to minus of F3 from 2. That's what they call action-reaction. So remember, the third law is a little bit different than the first and second law, in the sense that the third law is being applied not on a particular system of mass m, this one, but at the junction of two systems which are connected to each other. So we can do the same thing on object 1. If you apply Newton's second law on object 1, object 1 will feel a force pulling in this direction. then it will feel a bunch of, another force pulling in the other direction. Let's call it Z. Now if we do Newton's third law at the junction between object 3 and object 1, then we know that this Z is indeed the force due to object 3 into 2. Similarly, we can call R, which was the external force acting on 3 due to 1. Oh wait, I'm sorry, Z must be the force of 3 into 1. So R, remember, was the force due to 1 into 3. And we can see clearly that this point is the same as this point. Therefore, R is the same as minus Z, or F3 into 1 is the same as minus F1 into 3, or vice versa.